sklearndecompositionKernelPCA. Description: KernelPCA is a nonlinear dimensionality reduction technique that uses kernel functions to project data into a higher dimensional space, where linear methods can be applied to find principal components. It allows for capturing nonlinear relationships in the data and finding meaningful lower dimensional representations. Inputs: X, a NumPy array or pandas data frame containing the data to be decomposed. Each row represents a data point, and each column represents a feature. Kernel: the kernel function to be used. The default is RBF, radial basis function. Other options include linear, poly, sigmoid, and custom kernels. Outputs: X transformed, a NumPy array containing the transformed data in the lower dimensional space. Each row represents a transformed data point. Lambdas, a NumPy array containing the eigenvalues of the kernel matrix. These values represent the variance explained by each principal component. Steps: Kernel computation: the algorithm computes the kernel matrix, which represents the similarity between all pairs of data points based on the chosen kernel function. Eigenvalue decomposition: the kernel matrix is decomposed using eigenvalue decomposition. The eigenvectors associated with the largest eigenvalues correspond to the principal components. Projection: the data is projected onto the subspace spanned by the selected principal components, reducing its dimensionality. Metrics: variance explained: the proportion of variance explained by each principal component, represented by the eigenvalues. Reconstruction error: the difference between the original data and the reconstructed data after dimensionality reduction, measured using metrics like mean squared error. Visualization plots: sklearndecompositionKernelPCA. This plot visualizes the eigenvalues in descending order, highlighting the importance of each principal component. Projection plot: this plot shows the transformed data points in the lower dimensional space, visualizing the relationships between them. Fine-tune parameters: n components, the number of principal components to retain. This value controls the level of dimensionality reduction. Gamma: the kernel coefficient for RBF, poly, and sigmoid kernels. It influences the width of the kernel function and the non-linearity of the projection. Uncertainty methods: confidence intervals based on the variance explained by each component. Confidence intervals can be computed to quantify the uncertainty in the estimated principal components. Challenges and fixes: high computational cost: computing the kernel matrix can be computationally expensive, especially for large datasets. Sample use case that resulted in challenge 1: when dealing with tens of thousands or millions of data points, the time required for kernel computation can become prohibitive. Fixes to challenge 1: Nystrom approximation: this technique approximates the kernel matrix using a subset of data points, significantly reducing computation time. Randomized kernel approximation: this approach uses random projections to approximate the kernel matrix, further reducing computational cost. Overfitting: choosing an overly complex kernel can lead to overfitting, where the model performs well on the training data but poorly on unseen data. Sample use case that resulted in challenge 2: using a high-degree polynomial kernel with a large dataset might lead to overfitting, as the model becomes too sensitive to the training data. Fixes to challenge 2: regularization techniques like L1 or L2 regularization can be applied to the kernel matrix to prevent overfitting. Cross-validation: splitting the data into training and validation sets and using cross-validation can help identify the optimal kernel complexity.